Okay, lecture 13, another application of differentiation. This time I'm talk about the expansion here. Okay. Well, before we start talking about expansion, let's look at the computation in computer. Well, I guess you're familiar with the fact that the computers can only perform plus, minus, and product and division. But those two are actually performed by using plus and minus, blah, blah, blah. But anyway, so that's all. So probably you must have asked this one already. How sinusoidal, exponential, and other complex functions are computed in a computer? If that is the only thing they can do it. Sine? How can you compute sines and cosines and etc., etc.? And the answer is that we use approximations here that require plus, minus, multiply, and divide only. If we use those approximations, computers can compute those functions. So how? Question is how? How can we come up with the approximations? And the answer is use power series. And start from sequence, and then series, and then get to the power series. Power series is something, but to get to that point, we start from something which is here. A sequence is just a bunch of numbers, one after another. And there are infinitely many of them, so this is called the infinite sequence or just a sequence. Finite sequence is the one which terminates at a finite number. And if you add all of those elements in sequence, then that is called a series. Infinitely many of them, infinite series, of course, but most of the time we don't even say infinite. When we say infinite series, it's infinite series. In summation form, this is what we use. And if you have only finite of them, that's it. Okay? And out of those special series are power series, where alpha 1, alpha 2 becomes alpha 0, alpha 1x, alpha 2x squared, alpha and n squared, blah, blah, blah. So general term in series is the power of x. And again, once again, you terminate here, you have x to the next power. But the finite series or infinite series, you only use addition, subtraction, and multiplying constants. That's all you needed, right? So computers can do it. Infinitely many of them, probably not. So probably that this is what you do. And this one here, if you look at it, this is nothing but the power series is a polynomial. It's just a polynomial, right? Any sort of polynomial. So we all know that. Even computers can compute that. But when you have infinitely many of them, you have a problem of convergence or divergence. Add them together, many of them, so the sum may go up to infinity or go down to minus infinity. That's divergence. So we have to look at that. If it converges, then this entire sum becomes a number, and the power series becomes function of x. Some function of x. Okay? So the convergence is important. If it converges that, so we can use that. Okay? Engineers can use those. But we always have to look at the convergence. We, meaning mathematicians. So mathematicians will talk about, well, they spend a lot of time in proving the convergence or divergence of series, but we'll leave that to the mathematicians. We only said that the series converges if the quantity called the remainder term goes to 0 as n goes to infinity, but that's just about it. So for us engineers, we assume convergence or limit x to the region of convergence. Region of convergence. Okay, so therefore, we always can assume that series can converge. And the power series, the use of the power series is this one here, Taylor series. The Brooke Taylor formalized this one in 1715, and the assumption is if f of x, a function, is analytic, meaning that you can differentiate as many times as you like, then f of x can be written in terms of this power series where the coefficients are given by this one here. Parenthesis n is the same as nth derivative. So this one here is nth derivative, and nth derivative is evaluated at 0. So that's this, evaluated at 0. Okay. The convergence only where the remainder term goes to 0, as I said. So some power series, Taylor series converge for any x, or some converge only in certain region. That is called the convergence region. Okay. So therefore, let's take a look at the exponential function. Example. Well, it is always important to look at example whenever you try to understand something new. So exponential function is used so often. Besides, in Taylor series, you have to compute the derivative, right? So therefore, exponential function is easy. All right. So the first derivative, the coefficient a comes out. Second derivative twice, so a squared. Nth derivative n times, so a to the nth power. So that's easy. And from this one here, evaluated at 0, e to the 0th power is equal to 1. So consider that all those e thing drops. So you only have a squared, n squared, etc., etc. So what happens is that this becomes that. Just n squared. That's all it remains. So if you like, you can combine this n squared and x squared and write in this form as well. That's easy. But if you look at this way, it's easier to understand what's going on, right? The n is equal to 0, 1 over 0 factorial, 0th power is equal to 1. Haha. Other thing here. 0 factorial is equal to 1. That's something which, well, looks odd, but that is true. And there's a way to prove it, but I'm not going to do it here now. You can ask your teacher, or you can send me an email. And the second one is 1 factorial, the first power, that's 1, the second power, and 2 factorial, 3 factorial, 4 factorial, etc., etc. So this series converges for all x. Great. Okay, this is one of the series which one of a few, very small number of Taylor series expansion which converges for all x. I'll give you 2 more which converges for all 2x. Let's look at the graphs. Okay, let's draw graphs. Well, how do I draw graphs? This is the original exponential function. Okay, and what I do is I pick up only 1 term or 2 terms, 3 terms, 4 terms, blah 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 blah, and look at how good the approximation is. The first one, 1, not really good. Second one, this, still not really good. Third one, getting better. Fourth one, wow, it's getting close, except those negative part. The fifth one here, that's up to the 4th power, that's mighty close. And up to the 5th power, you get very close except this portion here, right? And if I put everything together, you get this one there. So as you can see, from here to there, approximation up to the fifth power is very good. And that becomes more error here. But so the approximation is good in certain range of x and not so good in other ranges of x. But it converges. That's important. Okay, let's apply that to many of them, but one particular application which is very, very interesting. Well, we had e to the a theta, so let's set a is equal to j. Of course, we know that j squared is equal to negative 1, cube is equal to negative j, the fourth power is 1, fifth power j. Go back again. So it circulates. Okay? So therefore, this is 1j minus 1 minus j, 1, j, blah, blah, blah. So we have real, imaginary, real, imaginary, real, imaginary. So we put together the real part and we put together imaginary part. We get this one here. And can you tell where I'm heading? Of course, you can tell. Euler's formula tells you that this one here is cosine theta plus j sine theta. And that is equal to that. So, by comparing real and imaginary parts, two complex numbers are equal to each other if and only if real part and imaginary parts are equal to each other. So, cosine theta is this and sine theta is equal to that. So, we got two power series for cosine theta and sine theta, which can be used by a computer to compute cosines and sines. Super. Of course, you can start from the definition of the Taylor series and compute the first derivative, second derivatives at 0, blah, blah, and you can get those. But Euler's formula gave us a magic. That's why I like Euler's formula. Okay. So as the exponential function, let's look at the approximation for sines and cosines since we have the power series. Well, the first power, second power, third power, fourth power, fifth power, sixth power, not six, but only the odd powers, so 1, 3, 5, 7, 9, 11. Here, cosine theta, 0th power, second power, fourth power, sixth power, eighth power, and 10th power. Those are the, I'm going to talk about the Maclaurin series in the next slide, but those approximations are good around this point, 0, right? On this point here. And probably good up to somewhere around here, the pi, here, somewhere around here, pi. If I add 1, 2, 3, 4, 5, 6 terms, 1, 2, 3, 4, 5, 6 terms, it's good. Okay? So those approximations are good in 0 to pi, but since this is the odd function, and this is the even function, so it's actually good in this region here. Okay, so the Taylor series is this one here, but actually this is one special case of Taylor series which is used so often. The general Taylor series is a little bit different. Okay. And this one here is so useful that this one has a name called the Maclaurin Series. Maclaurin came up with this series and Taylor generalized that into this. Expansion at x is equal to a. Then this one has this form here. Can you see the difference here? we had 0, that we now have a. And instead of x, we have x minus a. And compare these two, you can tell that this x was actually was x minus 0. So as you can see, this is a special case of that one when a is equal to 0. And this, the general Taylor series of expansion at x equal a is useful for the neighborhood of x equal a, locality, somewhere close to x equal to a. So sometimes you want to have function close to a certain value, not 0. Then what you can use is this one instead of the other one. Well, let's do the example. All right. Let's look at the finite one. I don't want to do too much computation, so up to the third power here. So we have a polynomial here, and let's compute the Taylor series expansion at x equal to 2. All right. So first one we need is f2, that is 12, and differentiated, you get 3x squared plus 6x minus 6. Evaluated at 2, you get 18. And you differentiate that one more time, you get 6x plus 6. So second derivative evaluated at 2 is once again 18. Third derivative here is only 6, so that's of course 6. Fourth derivative, differentiate 6, then that's equal to 0. Fifth derivative, of course, differentiating 0, that's 0. So there's gone, all gone, up to here. So put into this the Taylor series expansion. This is f of 2. This is f first derivative at 2 times x minus 2. And this is second derivative at 2 divided by 2 factorial x minus 2 squared. Then third derivative divided at 2 divided by 3 factorial times x minus 2 cubed. And comparing these two, you have this. Do you believe this? Well, it is very easy to check it by just computing those this cube and this squared and put them together. Then you get the original one. Check it. And also, I recommend you to do this. How about the Maclaurin series? Expanding at x is equal to 0. What do you think you're going to get? Try that. It's very interesting. Well, you may already know the answer, but try it. Okay. Applications. This is the first application. Well, let's set x minus a is equal to dx and a is equal to x0. So those a's and x minus a's you can replace by x0 and dx. And because if we define this, then x becomes that. So that becomes this. And if you write first 3 terms of this summation, you get this one here, and you have fx0 here, so you move that to the other side. You have f x0 plus dx minus f x0. That's nothing but dx. Well, actually, this is delta x, right? So this equation says for well, this one, I'm going to talk about this one here in the coffee break. But what it says is if dx is very small, dx squared is too small. So forget about that, is what it says. So we ignore from here on. Then what you get is this. Okay? So the change in the function is due to the change in x variable are related by the derivative evaluated at that point. We have seen this before. Do you remember what this one was? This is actually the equation for fine adjustments, right? This happens to be the change in theta, and this happens to be the change in end effector position. So that relationship, we use differentiation to find it out. But if you look at the approximations, this is it. So approximation tells you that the equation we had developed was correct. So suppose that x0 is an extremum application 2. In that equation, what's going to happen? Okay, it should go the other way around, but since this is equal to that, okay, so this must equal to 0. Why? The reason is that otherwise df becomes both plus and negative for small dx. But let's look at this one here to be positive. Okay, then if dx is positive, this becomes positive. So dx positive, you're moving this way, and this is positive, so it goes up. And if dx is negative, goes this way, this is positive, so this entire thing becomes negative, so it goes down. Down and up. So the function must be moving like this. Is this an extremum point? No, it cannot be. The other way around is also true. If that is negative, then it should be like this one here. Once again, it is not an extremum. Okay, so this has to be 0. Okay, so from the expansion, you can find this one out. So at the extremum, this must be 0. Okay, if this is equal to 0, then df, the next term, this one, since this one is gone, so next term is this one here. And dx cube is too small, so forget about that, and given by this one here. Okay, so what can we tell from that one? Well, if df greater than 0, not if. This is greater than 0 if this is greater than 0. Why? Because this is dx squared, so that's always positive. So if this is positive, df is always positive. If this is negative, then that's negative. Okay? And if this is equal to 0, df is equal to 0, well, actually, question mark. So in this case, this is greater than 0, so like this, right? As you move away from that point, it goes up because df is greater than 0. So that means it must be minimum. And the other way around, this df less than 0, so it goes down regardless of the direction you go. So therefore, that must be maximum. And is equal to 0, inconclusive. Because that term is gone, so now this is not true. df is represented by 1 over 3 factorial, third order derivative evaluated at x0 dx cube. Okay? So once again, this is inconclusive. By looking at that, you cannot tell. So the second derivative condition we already had is okay, works. So from this expansion, you can confirm that what we had before is good. All right. Let's look at other series expansion, and after that, I'll talk about that smaller thing. Okay. Well, the Maclaurin expansion for this one here is very famous because this is 1 plus x squared, blah, blah, blah. The series is very famous, so I just wanted to give you this. And important part, well, it is easy to prove, by the way. You multiply fx and this one, 1 minus x, both of them, then you can prove it very simply. But this has to converge, right? And as you know, if x is greater than 1, square is greater, cube, it goes up to infinity. So this one is good only for this one here. Absolute value of x is less than 1. Less than 1 cannot be equal to 1. If you add 1, infinitely many of them, that's going to be infinity. It's okay. So that's the region of convergence. And another one is called the Fourier series here. Oh boy. This one has so much applications. So you will use this in many different disciplines. Well, looks like this one here. Oh, well, first of all, Fourier series is varied for the periodic function period t. So it repeats itself every t seconds. Okay, 2 seconds. Periodic. Haha, I cannot pronounce periodic. Then this is equal to that given by cosines and sines. Omega 0 is called the fundamental frequency, which is given by this one here. So from here to there, that's t, and omega 0 is this, 2 pi over t. How to compute an and bn if time allows, and I don't have time. So this one will be covered in calculus course. Application, frequency response. You know anything about frequency response? Are you a fan of music? Then you know a thing called the equalizer. Equalizer has lots of those graphs, goes up and down, different frequency. So frequency response. Frequency, let's look at this one here. Omega 0, 2 omega 0, 3 omega 0. So frequency goes up, 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 up. So this is exactly what we use for frequency response. Fourier series. All right, as I promised. Coffee break, what's the difference between this one and that one? Well, one of them we already know means dx is smaller than 1. Yeah, that's smaller than 1. And then you have 2 smaller than. So it must be much, much smaller than 1. And the question is, of course, what we mean by much, much smaller than 1. Well, actually what it means is this. If this is much, much smaller than 1, then compared to 1, this is negligible. You can get rid of that. This is equal to 1. From engineering point of view. Okay? So, like this one here is equal to dx for m greater than 0 because this one here is dx to the nth power 1 plus dx to the mth power. And of course this one here, you can forget about it, right? And example. Let's get rid of this one here. Dx is equal to then 10 to the minus 6 power. Dx squared is 10 to the minus 12 power. Can you tell why I'm using those two? I'll show you why. But anyway, engineering sense is there are 10 to the 6 difference. That's within an error. When you do make any measurements, if one value is 10 to the 6 times the other, the first value, you can forget about that. 10 to the 6 is too large a difference. And this one happens? Yeah, it happens. Where does those value come from? Example is a capacitor. 1 microfarad capacitor is the regular one we use. That's 10 to the minus 6 farad. 1 picofarad capacitor, we use that often too. That is 10 to the minus 12 F. So that kind of difference can happen in engineering so often. So what I can say is that 10 to the minus 12 can be ignored compared to 10 to the minus 6. That's what this less than means. All right. That is actually the end of this lecture here. And next time I will talk about another application of differentiation. Thank you.